How safe is flying? You might have thought that 2014 was a bad year for flying. There were four highly publicized accidents. The still mysterious disappearance of Malaysia Airplanes flight Airlines flight 370 in March. The shooting down of Malaysia Airlines flight 17 hour Ukraine in July. The Air Algeria flight 5017 crash in Mali. Also in July, with a total of 815 dead. And finally Air Asia flight QZ 8501 falling into the Java Sea in December, but according to Ascend, the consulting branch of flight global that monitors aircraft efficiency 2014 in fact had the best accident rate in history. One fatality per 2.38 million flights. True, Ascend did not count the downing of MH flight 17, which was an act of war, not an accident, including that inside incident as the International Civil Aviation Organization does in its statistics raises the rate to 3.0, still much lower than between 2009 and 2011, and the subsequent years were safer still. Fatalities declines to 474 in 2015, 182 in 2016, and to just 99 in 2017. And there was a reversal in 2018 with 11 fatal accidents and 514 deaths, still lower than in 2014, including the Lion Air Boeing 737 7 Max falling into the Sea of Jakarta in October, and in 2019, despite another Boeing 737 Max crash, this time in Ethiopia. The total number of fatalities was half of those in 2018. In any case, it's better to personalize the problem by putting it in terms of the risk per manager per hour of flight. The necessary data are in the annual safety report by the International Civil Aviation Organization, which covers large jetliners as well as smaller commuter planes. In 2017, so far the safest year in commercial flying. Domestic and international flights carried 4.1 billion people and logged 7.69 trillion passenger kilometers with only 50 fatalities, with the mean flight time at about 2.2 hours. This implies roughly 9 billion passenger hours and 5.6 by 10 power of minus 9 fatalities per person per hour in the air. But how low is this risk? The obvious measuring stick is general mortality, the annual death rate per 1,000 people in affluent nations. That rate now ranges between 7 and 11. I will use 9 as the mean because the year has 8,760 hours. This average mortality prorates to 0.00001 or 1 by 10 power of minus 6 deaths per person per hour of living. And this means that the average additional chance of dying while flying is just is just 5/1000th of the risk from of the risk of simply being alive. Smoking risks are 100 times as high. Ditto for driving in a car. In short, flying has never been safer. Obviously, age-specific mortality for older people is much higher. For individuals, for individuals of my age group, our 75. It is about 35 per thousand or thousand or 4 by 10 power of minus 6 per hour. That means that of a million of us, four will die every hour. In 2017, I flew more than 100,000 kilometers, spending more than 100 hours aloft in large jets belonging to four major airlines whose last fatal accidents were respectively in 1983, 1993, 1997, and 2000. In every four aloft, the probability of my demise wasn't even 1% higher than it would have been had I stayed on the ground. Of course, I've had white knuckle moments. The most recent one was in October 2014, when my Air Canada Boeing 767 headed into the turbulent fringes of a mega typhoon that was crossing our Japan. But I never forget that cute hospital rooms are what should really be avoided. Although the latest assessment of preventable medical errors has greatly reduced the previously exaggerated claims of that risk. hospital hospitalizations remain associated with increased exposure exposure to bacteria and viruses, elevating the risks of hospital acquired acquired infection acquired infections, particularly among the elderly. So keep on flying and avoid hospitals. Which is more energy efficient, planes, trains, or automobiles? I have no animosity toward cars and planes. For decades, I have depended for local travel on a succession of reliable Honda Civics, and for years I have flown intercontinentally, at least 100,000 kilometers annually. At these two at these two extremes, drive to an Italian a flight from Winnipeg to Tokyo. Cars and planes rule. Energy 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 intensity is the key. When I'm the only passenger in my Civic, it requires about 2 megajoules per passenger kilometer for city driving. Add another passenger and that figure drops to 1 megajoule megajoule per kilometer, comparable to a half empty bus. And jet airliners are surprisingly efficient, commonly requiring around 2 megajoule per kilometer. With full flights and the latest airlines designs, they can do it at less than 1.5 megajoule per kilometer. Of course, public transit trains are far superior at high passenger loads. The best subways need less than 0.1 megajoule pkm. But even in Tokyo, which has a dense network of lines, the nearest station may be more than a kilometer away, too far for many less mobile people. But none of these modes of transportation can equal the energy intensity of intercity and high-speed trains. These are typically on roads of 150 600 kilometers. Other models of Japan's pioneering bullet train and the Shinkansen, meaning new main line, had an energy intensity of around 0.35 megajoule ppm. More recent fast train designs, the French TGV and German ICE, typically need just 0.2 megajoule ppm. That's an order of magnitude less than airplanes. No less important, high-speed trains are indeed fast. The Lion Marcel TGV covers 280 kilometers in 100 minutes. 100 minutes downtown to downtown. In contrast, the scheduled commercial flight time for about the same distance, 300 kilometers from New York's LaGuardia Airport to Boston's Logan Airport is 70 minutes. And then you must add at least another 45 minutes for checking in, 45 minutes for the ride from Manhattan to LaGuardia, and 15 minutes for the ride from Logan to downtown Boston. That raises the total to 175 minutes. In a rational world, one that valued convenience, time, low energy intensity, and low carbon conversions, the high speed electric train would always be the first choice for such distances. Europe is natural train country, and it has already made that decision. Yet even though the United States and Canada lack the population density to justify dense networks of these connections. They do have many city pairs that are suited for fast trains. Not a single one of those pairs has a fast train, however. Amtrak's Acela line between Boston and Washington D.C. Does not even remotely qualify, as it averages just a measly 110 km/h. This leaves the US and also Canada and Australia as the outstanding laggards in rapid transportation. But there was a time when America had the best trains in the world. In in 1934, 11 years after General Electric made its first diesel locomotive, the Chicago, Burlington, and Quincy Railroad began to run its streamlined stainless steel Pioneer Zephyr, a 600 horsepower, 600 horsepower, 447 kilowatt, 8 cylinder two-stroke diesel electric unit. This power made it possible for the Zephyr to beat the speeds of today's Acela with an average of 124 km/h on the more than 1,600 km long run from Denver to Chicago. But there is now no realistic hope that the US could ever catch up with China at 29,000 kilometers of high-speed rail. That country now has the world's longest network of rapid trains connecting all major cities in its populous eastern half. Food energizing ourselves. The world without synthetic ammonia. By the end of the 19th century, advanced in chemistry and plant physiology made it clear that nitrogen is the most important macronutrient element needed in relatively large amounts in crop cultivation. Plants also require phosphorus and potassium, are the other two macronutrients, and various micronutrients, elements ranging from iron to zinc, all needed in small amounts. A good harvest of Dutch wheat, 9 tons per hectare, will contain about 10% protein or 140 kilograms of nitrogen, but only about 35 kilograms each of phosphorus and potassium. Traditional farmers supplied the needed in nitrogen in two ways: by recycling any available organic materials, stalks, leaves, human and animal waste, and by rotating grain or oil crops with leguminous plants, cover crops such as alfalfa, clovers, and wedges, and food crops such as soybeans, beans, peas, and lentils. These plants are able to supply their own nitrogen because bacteria attached to their roots can fix nitrogen, convert it from the inert molecule in the air to ammonia that is available to growing plants, and they also leave some of it behind for the following grain or oil crop. And the first option was laborious, especially the collection of human and animal waste and fermentation and application to fields, but manures and night soil had relatively high nitrogen content, commonly 1-2% compared to the less than 0.5% nitrogen in straw or plant stalks. The second option required crop rotation and prevented continuous cultivation of staple grain crops, be it rice or wheat, as the demand for staple grains grew with an expanding and urbanizing population. It became clear that farmers would not be able to meet future good needs without new synthetic sources of fixed nitrogen, that is, nitrogen available in forms that can be tapped by growing crops. And the quest to do so succeeded by 1909, when Fritz Haber, professor of chemistry at Karlsruhe University, demonstrated how ammonia and NH3 could be made under high pressure and high temperature in the presence of metal catalyst. The First World War and the economic crisis of the 1930s slowed down the worldwide adoption of the Haber-Bosch process, but the food needs of the growing global population from 2.5 billion in 1950 to 7.75 billion in 2020 ensured its massive expansion from less than 5 million tons in 1950 to about 150 million in recent years. Without this critical input, it would have been impossible to multiply staple grain yields. See multiplying wheat yields. This page and feed today's global population. Synthetic nitrogenous fertilizers derived from Haber-Bosch ammonia, solid urea. Urea is the most common product currently provide roughly half of all nitrogen required by the world's crops, with the rest supplied by rotations with leguminous crops, organic recycling, manures and crop residues and atmospheric deposition, because crops now supply about 85% of all food protein, with the rest coming from grazing and aquatic foods. This means that without synthetic nitrogen fertilizers, we could not secure enough food for the prevailing diets. Of just our 3 billion people, more than the combined population of China, where synthetic nitrogen already provides in excess of 60% of all inputs, and India, and with the growing growing populations in parts of Asia and in all of Africa. The shares of humanity dependent on synthetic nitrogen will soon rise to 50%. China still makes some ammonia by using coal as the feedstock, but elsewhere the Haber-Bosch process is based on taking nitrogen from the air and hydrogen from natural gas, mostly CH4, and also using the gas to supply the high energy requirements of the synthesis. As a result, worldwide synthesis of ammonia and the subsequent production, distribution, and application of solid and liquid nitrogenous fertilizers are now responsible for about 1% of global greenhouse gas emissions, and we do not have any commercial non-carbon alternative that could be deployed soon on the required mass scale of making nearly 150 million tons of NH4 a year. Immediately more worrisome are large nitrogen losses, volatilization, leaching, and denitrification resulting from fertilizer use. Nitrates contaminate fresh waters and coastal seas, causing the expansion of dead zones. The atmospheric deposition of nitrates acidifies natural ecosystems, and nitrous oxide N2O is now the third most important greenhouse gas following CO2 and CH4. A recent global assessment concluded that the nitrogen utilization efficiency has actually declined since the early 1960s to around 47%. The more than half of the applied fertilizer is lost rather than incorporated into harvested crops. Demand for synthetic nitrogen is saturating in affluent countries, but large increases will be needed to feed some 2 billion people to be born during the next 50 years in Africa.
to cut future nitrogen losses, we should do everything possible to improve the efficiency of fertilization, reduce food waste, and adopt moderate meat consumption, and even that will not eliminate all nitrogen losses, but that is the price we pay for having gone from 1.6 billion people in 1900 toward 10 billion by 2100. Multiplying wheat yields. What is the average wheat yield in central France, in eastern Kansas, or in southern southern Hebei province? Few people besides the farmers, those who sell the machines and chemicals, the agronomists who counsel them, and the scientists who develop new crop varieties have the answers ready. This is because all but a tiny share of the population in modern societies has become almost completely detached from anything to do with crop cultivation, except of course for eating the products. Every crunchy baguette, and every croissant, every hamburger bun, and every pizza, every steamed bun, mantou, and every strand of twisted and stretched lemon noodles starts with wheat. But even those people who consider themselves well educated and widely informed, and who could point out the improved performance of cars or the rising capabilities of computers or cell phones, would have no idea if the average 20th century staple grain crops had tripled, quintupled, or risen by an order of magnitude, and yet it is these multiples, not those of mobile phone capability or cloud storage, that have made it possible to nearly quintuple the global population between 1900 and 2020. So, what happened to the yields of wheat, the world's dominant staple? Its traditional uh, yields were both low and highly variable, but reconstructions of long-term trends remain arguable. This is the case even with relatively well documented for nearly a millennium history of English wheat yields, which were usually expressed as returns on planted seed following a poor harvest. Up to 30% of the yield had to be saved for the next year's seed, and the share was commonly no less than 25%. Early medieval harvests were often as low as 500-600 kilograms per hectare. That is as little as 0.5 ton. Yields up to 1 ton per hectare became common only by the 16th century, and by 1850 the mean was about 1.7 ton 1.7 ton roughly tripling since 1300. Then came a combination of measures, crop rotation, including nitrogen fixing, legumes field drainage, more intensive manuring, and new crop varieties that lifted the yields above 2 tons HA at a time when French yields were still only 1.3 tons HA, and America's extensive Great Plains fields produced only about 1 ton HA, and that was the countrywide mean even as late as 1950. Decisive improvement came after centuries of slow incremental advances. Only with the introduction of short-stalked wheats, traditional plants were tall, nearly as tall as Bruegel's peasants, cutting them with scythes, producing 3 to 5 times more straw than grain. The first modern short-stalked wheat based on East Asian plants was released in Japan in 1935. After the Second World War, it was brought to the US and given to Norman Borlaug at CIMMYT, the International Maize and Wheat Improvement Center in Mexico, and his team produced two high-yielding semi-dwarf varieties yielding as much grain as straw. In 1962, Borlaug won the Nobel Prize. The world got unprecedented harvests. Between 1965 and 2017, the average global wheat yield almost tripled from 1.2 to 3.5 tons HA. The Asian average more than tripled from 1 to 3.3 tons HA. The Chinese mean more than quintupled from 1 to 5.5 ton HA, and the Dutch mean already extraordinarily high 2 generations ago, more than doubled from 4.4 to 9.1 tons HA. In that time, the global wheat harvest nearly tripled to almost 775 million tons, while the population increased 2.3-fold, raising the average per capita supply by about 25% and keeping the world comfortably supplied with wheat flour for crusty German Bauern bread made with wheat and rye flour, Japanese udon noodles with flour, a little salt, water, and classic French meal fuel, the puff pastry needed for the sheets is just flour and butter and a bit of water. But there are concerns. Average wheat yields have been leveling off not only in the EU countries with the highest productivity, but also in China, India, Pakistan, and Egypt, where they remain well below the EU mean. The reasons range from environmentally driven restrictions on the use of nitrogenous fertilizers to water shortages in some regions. At the same time, wheat yields should be benefiting from higher atmospheric CO2 levels, and agronomic improvements should close some of the yield gaps differences between a region's yield potential and actual productivity. But in any case, we would need substantially less wheat if we were to be able finally to reduce our our indefensibly high food waste.